It's a pleasure to be here with all of you and to be talking today. I know it's a little bit of a different hazard to earthquakes, but given where we are in California in the multi-hazard world, I think it's incredibly relevant. So before I get started, I want to thank the funders of this work, the Moore Foundation, NSF, and especially CAL FIRE, which funded our analysis and did a lot of the on-the-ground data. So we're going to be looking at drivers of risk to structures, and I'm going to talk about two things today, both in machine learning aided analysis using on-the-ground data and our new modeling tools to look at risk in communities. And there's a number of co-authors. It's been a big work over many years to put this together. So to start off, I want to talk a little bit about wildland-urban interface fires, or WUI fires, because it's not so much the wildfires that are giving the big destruction, it's when those fires get into our communities and burn houses down. And if you look at some of these numbers, they're dramatic. The Camp Fire had over 18,000 plus structures. Palisades and Eaton were about 6,000 plus each. There were 2 fires in LA, the Marshall Fire in Colorado, the Tubbs and Nuns Fire. This has been a continual trend, and it's getting worse. We saw this in Lahaina. The fires are no longer out in the forest. It's not this forest fire you think of. It's actually into our communities. And so these are developed areas, it's suburbia, where we don't think we have this sort of hazard. I'm sure this is very familiar to all of you. We don't recognize the hazard, yet they barrel through. And so our goal is to further understand the physics of these disasters and try to use them predictively to try to mitigate and prevent these future events from occurring. So this is the challenge, right? How do you model this? I mean, look at, this is the Tubbs Fire in 2017. This row of houses burned down, and then it stops. All the previous rows are completely burned down. Why did it stop? I mean, unraveling this, it is a spatial and time problem. It has to do with small features as well as large overall driving events. And so I'm going to break down some of those driving features and what we've done to understand them. So let's talk first, how do fires actually get from a wildfire, move into a community, and then within that community, spread within there? And there's 3 ways we've broken this down. The first of which is radiation. And this is what everyone thought is important in fires. You have a big fire, it radiates the house, and depending on the distance, it can ignite it. Now what we've done is we've done something called defensible space. So if we actually take and move things away from the house that are flammable, we no longer have this radiation problem. Now this is a problem if your neighbor's house is unprotected and sitting there. But so long as you have about 30 feet or a little greater separation, you actually do pretty well about preventing ignition. Direct flame contact is what we define as the small things. Let's say you have a little fire coming up to the house. It treks along your wooden fence. The wooden fence has flames directly up to your siding, and you lose the house. And this is actually very common with wood fences. And California is now trying to pass their 5-foot regulations to keep all the small materials, regardless of what they are, 5 feet away. Finally, embers or firebrands. This is actually the most common source of starting fires into a community, because there's usually separation between wildland and the community itself. So those small smoldering embers, they're almost like little pieces of charcoal, fly, accumulate, they find receptive fuels, they land and they ignite. And there's millions. They're everywhere. And so all you need is to find a receptive fuel, and that 1 in a million chance happens again and again. Now, we can prevent this as well. We can think of different things we have around the house to prevent it, but these are very small particles in fires. And you can see this is, I did this because it's UC Davis fire, so this is a UC fire, but you could just see it's a blizzard of embers outside. Whoops. So here's the 2 ways we can think of mitigation. 1, move fuels and flammable materials away from the structure. The 5-foot zone, we think of everything. 30-foot zone, we don't want flames that can get close to the house. And the 100-foot zone, just try to minimize that fire. You don't have to have a barren landscape, but you have to kind of space this and think of the physics. The second size is hardening. Try to make that home so if the fire isn't touching, you can prevent the flames from getting in. So think of your vents. Find mesh and screens so that embers can't get in. Windows that are double paned, so even if the fire gets close, it doesn't fracture them. Gutters that won't collect debris. Roofs that won't ignite. So, et cetera, all these things that we know are effective. The question, of course, is how effective are they? We keep touting all these recommendations, But we don't have that on-the-ground definitive, this is how effective this is, or how they interact with each other. And that's what we're going to talk about today. So first part, I want to talk about a data-driven WUI risk to structures. So we're going to utilize on-the-ground data of destruction, over 40,000 structures, and try to look at that and see, well, if we apply mitigation, can we calculate the risk reduction to structures? So this is really that missing link. Can we take the exposure, which we don't have because no one's actually there during the fire? Can we figure out how to figure out exposure? Can we then figure out what was there? And can we try to calculate what features were most effective and how to potentially mitigate future fires? So our challenge is, there's no quantitative data yet ranking this. And certainly there's, the data that we use, there's been some analysis in the past, but it's usually using linear analysis, correlations, or statistics. And these don't really capture the interrelatedness. So for instance, oh, I protected everything, I cleared everything, but I left my vents open. Well, embers will go through the vents, ignite your attic, and all is lost. It doesn't matter if you did everything else, you missed a critical thing in an area exposed to embers. We need a way to look at that interrelatedness. And we also need to understand what area is exposed to fire, what area is exposed to embers. And so the way we do this is to start with on-the-ground data. CAL FIRE has this damage inspection data set, Ground Truth. I've been working with them since 2014 as they do these collections after every fire, and it's gotten much better over time. Now they not only look at the structures that burned and any previous information they had, they also look at surrounding structures. So we have this nice comparative data set. We're going to have lots of remotely sensed data that we use, like LiDAR, which has surrounding vegetation and fuels. And finally, we're modeling exposure. So we're picking 5 of the biggest fires, that gives us a large data set, and we've remodeled them using the best available data to create the fire and ember exposure that was missing because no one had on-the-ground data. Then we look at the significance of different features. We're going to use machine learning and a SHAP analysis and kind of analyze those 5 fires and see what we learned. So this is just an example of the DINS data set. It covers the whole state, but we're focused on 3 Northern California fires here, kind of essentially around the Bay Area, the Camp Fire, and the Thomas Fire in Southern California. And that leads us here to over about 40,000 structures that are in our database. So it's a lot of structures. There's actually more from other fires, but many of them are small and it would take a lot of additional modeling effort, but we hope to do more of this in the future. So how do we combine and process? We start with the DINS, and the DINS data has data on roof, siding, windows, vent, the year built, lots of information about the structure, either from property records, from photographs, or actual on the ground. And we fill in the missing data. We look at defensible space using LiDAR. We have under 1 meter resolution for veg intensity for most of the fires we looked at. One, we had to do this visually. Very intensive, fun undergrad project for the summer. Structure separation. We have building layouts for the entire state, so we could look at the MS structure footprints and calculate that. Flames and embers. We actually reconstructed past fires. I'll talk about the model that we used and then use the outputs. And then we added undamaged structures where we didn't have that information. So it's very important to know what structures did burn and compare those that didn't. So we had to add some structures in. And then we compared those fires that we used not only to the damage data set, but also to aerial imagery and satellite imagery. So for defensible space, I mentioned that we used LiDAR, so you could just see a visual example. Clearly no defensible space. Great defensible space, right? Lots of space that's cleared. Not everything is just quite this clear, but when we use LiDAR, it gives us not only, so we have the building locations, we have vegetation locations, and we see pretty fine resolution up to the house. Now we may miss small things that are in defensible space, but at least for the vegetation, it gives us a good idea of the separation between the structure and nearby vegetation to fine resolution. Fire modeling is difficult though. What we currently do for fire is take vegetation, weather topography, and we have models for the fire on the surface, the crown, the embers, and we currently use a model called Elm Fire. It's an Eulerian level set model to run the wildfire And from that, we get the spread rate, ember cast, and flame length. Of course, our fires are not just in the wild, they're around structures. So for this first analysis, we used a simple model that you might have heard of Hamada, which is from the 1950s, post-earthquake. And we've improved that, which I'll talk about later, but we use that so that the fires don't stop, and we still get an ember fire load. Just as an example of why this is necessary, we ran the campfire without any WUI. Everything that's a building is marked non-flammable in federal data sets for wildland fuels, and you can see how the fire just stops. And so this clearly is not accurate, and so we need to be including WUI structures to get an accurate model. And I'm not going to talk about it today, but the Hamada model is very simplified. It's not optimized for WUI, but in our case, we're able to actually spread the fire. It's very quick, so that we still get a flame and ember exposure to the structures. It doesn't really matter how much flame and ember exposure. We don't see strong correlations. It's whether you do get flame and ember exposure to that area. And so some examples. This is the Kincaid fire in 2019. It's a little hard to see, but these are all the DINS losses. And then you can see our modeling. So this here is showing time. We can't pick up things where, like, in the next day that there actually was some suppression. But for the early stages when it impacted structures, we're pretty good, over 80% accuracy. And of course, it's not going to be perfect. The other thing is that the whole extent where the wind is blowing is covered with embers. And so we get a really strong correlation to see the areas that are actually covered with embers. And the same thing for the campfire. You saw that earlier plot where the campfire just didn't model anything into the community. Now you can see how the fire goes straight through the community. Now, unfortunately, it'd be wonderful to have multiple fire lines so we can map it over time. We've got like one satellite image. And that's just the nature of it. There actually is a new satellite network that Google and Moore Foundation helped launch just up a couple weeks ago. And when that gets up, hopefully we'll get better resolution and better time. So to get the significance, we tried to use some classification methods and fit machine learning models that are going to fit our data. The hardest part actually was not that modeling, but cleaning and preparing. We had to use imputation because there's a lot of NaN values. Someone is literally on the ground in this smoking mess, in a mask, trying to figure out what happened here, and they don't get all the data. But the surrounding houses are usually built at the same time and have the same features. And so we tried to use best practice data science methods to imputate, also to look at standardized, to add additional data to look up. And so this took a year or two of efforts to clean up the data set so that things were clean and usable. Then we looked at 4 models. I mean, we looked at more, but we presented data for these 4 that we finally arrived. And we see that XGBoost showed better results in overall accuracy, and then ran it through a Shapley additive explanation, or SHAP analysis, to try to understand what feature interrelated is most important. And so this is a result of the analysis where we actually stacked all the data from all of these. And it may or may not have been expected, but structure separation is by far the most important. And this kind of makes sense. All of these fires are very large. They move through communities. And what's the most predictive factor is if you have a fire in your community and you're right next to other structures that can be burning, it's much more likely that yours will too. But siding also plays a role. The hardening you do on the structure is very important, and siding is going to be one of the most important factors protecting your house from your neighbor's house, impacting it. The year built is a confounding variable because different construction practices are used at different years, and then also buildings degrade. And so it's hard to kind of break out year built. But the nice part is that year built is a data piece that you have for all structures. We also see that flame length and ember deposited is still important, even though it is not the most important, right? So this varies from a lot of like the fragility curves that you're maybe used to. A lot of what happens for a certain building type is you see that the exposure is going to be very, very important. But it's not necessarily in wildfire. Once it gets to the community, the specific amount of flame and ember exposure doesn't matter as much as the susceptibility of the house and dependence on the neighbors. And this is what insurance struggles greatly with. What your neighbors do affects you so much. And then other factors, the roof, the vent screen, vegetation separation, that defensible space, that's still important, and we'll see there's some interesting interaction there. I just want to highlight as well that it doesn't stay the same on every fire. For instance, the Tubbs fire, flame length is actually an important variable. And that's because the Tubbs fire first burned a lot of homes down in rural areas and then moved to suburban. And if the fire never got to your home in the rural area, it made a big difference. Whereas once it was in the suburban area, it eventually moved through those whole communities. So there is some physical aspect of how the layout and how that fire progressed will change which variables are most important. So I'm not going to talk about each fire, but as we see through each of them, we generally have most of the same trends. Separation, year-built flame length tend to be among the most important, the siding. And you can't really just take one out and remove the others. All of them do play an important role, and depending on the layout of the community, have different impacts. Now, because we did this XGBoost model, we actually had a data-driven model for which structures would burn down if they're impacted by fire. And it had about 82% accuracy, then testing it on other fires. We could do something cool with this, though. What do we say? What if we actually took those old fires and we protected those structures? So this is initially, we had 80% of those structures destroyed. What if we just applied the siding, the vents, and the hardening? That goes from 20%, now 25% of the structures survive. What if we also do hardening and we clear the zone 0, that 5 foot, that closest area? Suddenly we go from 25% to 40% surviving. It is a huge jump in survival just by doing these small changes, which are not very expensive, in the 5-10K max range per house. And then if you continue to do defensible space, we get up to 48%. Now, this is the fact that we can't change structure spacing. We can't change the layout and pick up a house. But even doing the things that are recommended, we may not be able to completely change our outcome, but we can still make a significant impact in doubling the survivability. Now, I just want to take the last few minutes and mention that a data-driven model is great, but it doesn't really give us the physics of what's happening, and it doesn't let us figure out the most optimized way to lay out and to use communities. And so what we've done is develop something new, a wildland urban extension, that builds into current wildfire models so that the models don't stop at the communities. So you saw that we tried the Hamada model, and it's not really optimized for WUI. What we need is a model that goes from wildland into a structure, from the structure, spots back, and that they all interact. And we built that. And so what this has is direct flame contact, radiation, and spotting firebrands. It spreads through structures, incorporates mitigation, and links these together, and integrates within current risk and management frameworks. And essentially what this is, right, is it's just so we can talk from wildfire spread to urban, urban back, and they all talk to each other, so that none of the models are significantly independent, but these have the feedbacks and the interaction. And so it really was just a matter of getting these to talk to each other, and now, of course, speeding it up, which we've been able to accomplish a lot in the last year or two. So it includes the ember landing probability, including defensible space, radiation, and ember. And so embers are empirical, but they're probabilistic. So all models are run with hundreds or thousands of scenarios, but these are landscape scale, and they're sort of flat. It's like a checkerboard. We don't incorporate weather. This allows us to run those models fast, and that's how current landscape fire risk analysis is done. But now it can include WUI too. And because we have coefficients for radiation, coefficients for siding, for the amount of flammable versus non-flammable material on the exterior, we have the ability to adjust fuel models for specific structures and to add more fine-grained details. And just as an example, this is the Thomas fire in 2017 with WUI spread. You can see we can get time of arrival, and it matches fairly well and looks a lot like what we've seen. But also we can extract the ember cast. Then we can look here, and we can actually get DFC. So this is direct flame contact. What are the heat fluxes of direct flame contact? Some areas with structures burned have none, because that wasn't driving, in this simplified model, where the fire went. In others, radiation is an important factor. And of course, the model can incorporate dual factors, which are igniting structures. So in conclusion, we found that there were a lot of interrelated factors, but structure separation, the way we've laid out our communities, is most important. So we need to find a way to take the other features and still try to draw that together and get the best practice to reduce risk in our communities. So it gives us now a data-driven model, and we have a more spatial model which we can run, and hopefully we can use this not only to do risk, but actually to do on-the-ground enhancements and changes to communities. Thank you.